So we just worked on 3 different methods of solving systems of equations. We started with graphing and then added in substitution and elimination. This section, we're really just kind of putting all those together and solving a little bit harder questions, mostly focusing on some word problems. So 6.4 applications of linear systems, starting with just the fact that, again, we've solved systems using either a graph substitution method or elimination method. And the best method used depends on what kind of questions you start with. So it depends on those given equations and how precise you want your answer. So those 3 different methods that we can choose, again, the way you want to break it down, if you want a visual display or when you want to estimate a solution, graphing is best there. So graphing we don't really use as often because, again, estimating means we won't have exact answers, but that does allow you to picture it a little bit better. Substitution when one equation's already solved for one of the variables or when it's easier to solve for one of those. So if I start with a variable, it's isolated or it's easy to isolate one quickly. And elimination is basically every other case. So coefficients where one variable is the same or opposites, or when it's not convenient to use those other 2 methods. So we've also seen that systems of equations are useful for modeling our word problems, and especially the ones we're going to be working on in 6.4 involve mixtures, rates, or break-even points, most common. So looking at a first example of a break-even point, what we mean by that is that's when your income equals expenses. So the graph shows the break-even point for one business. So again, if I have one graph for income, another graph for expenses, where they meet, that's again your break-even point where income and expenses are equal. And to the right of this graph, that's where income is higher than expenses. That's when you're making money. Before that, that's when you're losing money. So that's what they refer to Black Friday. That's where you start making money for your business for the year. So notice the values of Y on one line represents dollars spent on expenses, and the values of Y on the other line also represent dollars, but this time is income. So Y is used in both situations to express expenses and income. So both work for dollars. And we're using that fact in that first practice question. Puzzle Expert wrote a new Sudoku puzzle book. The initial costs he used to make that are $864. Binding and packaging each book costs 80 cents. The price of the book that they're selling that for is $2. We want to figure out how many copies it's going to take to break even for that business. So let's define our variables first. X we're going to choose to represent the number of copies we need to sell. And Y, just like in that last example, we could refer to dollars for both income and expenses. So it's best to start with 2 different equations for your income and your expenses. For expenses, your dollars, so Y is going to be equal to 80 cents for each book, plus $864 to start the business. So $864 in startup costs, and it also costs you the binding and packaging fee for every book, so that's your variable cost. Income, though, is a little bit simpler. You're just making a profit, you're selling those books for $2, so $2 for every book is just what we use for the income. Break-even point is, again, where I want your income and expenses to be equal. So this would be like your example of substitution. If I already have Y isolated for both, I can just set those equations equal. So now I just have an equation in terms of X. I just want to subtract and then divide, and I find my answer for X to be 720 copies. We weren't even asked how much money that would be 0 anyway, at the break-even point. But again, if I want income and expenses to be equal, I just have to set them equal using basically substitution and then solve for X. So in real-world situations, we might also have to do a few different things, such as consider what we call the constraints, so something that you're limited by in an equation. And once I solve an equation, we need to also consider the viability of this solution. For example, negative number of hours is not viable. A lot of negatives you're not going to see in real-life examples. So we have one down here where San Diego Zoo has 2 water tanks that are leaking in the panda exhibit. One tank contains 10 gallons of water, leaking at 2 gallons per hour. The second tank has 6 gallons of water and is leaking at 4 gallons per hour. So we need to find out when will the tanks have the same amount of water. So same thing, we have to set up a system of equations. We've got to define our variables first. So X we're going to say is the number of hours that it's going to take, and Y is the amount of water in each tank. Again, since they're both being measured for water, I can use Y in those 2 separate equations. So for tank 1, my amount of water, again Y, I start with 10 gallons, but I'm also losing 2 gallons every hour because it's leaking, so my equation is Y equals 10 minus 2X. For the second tank, I still am measuring the amount of water, so that's Y equals. I start with 6 gallons, this time I'm losing 4 gallons per hour, so that's minus 4X. Same as the last equation, if I want to find out where those have the same amount of water, I just want y to be equal, so I set those two equal to themselves. This is just basically substitution. And with those two equations being equal to each other, I just want to isolate for x. This time I have x on both sides, or actually I guess we did last time also. Just want to combine your x's. I combine them so that the x's are on the left. That means we want to subtract, so our constants are on the right. Finish by dividing, and we get x equals -2. But when we see that answer, remember we chose x to represent the number of hours it's going to take. If I say that -2 hours, they'll both have the same amount of water, that wouldn't really make sense. So we can say they will never have the same amount of water, since -2 hours doesn't really work for our example. And on our last page, we have a few more practice problems. So first one's talking about rowing upstream or downstream. So I row upstream at a rate of 2 miles per hour. I travel the same distance downstream at 5 miles per hour. We have to use that to figure out my rowing speed if the water was still, and also the speed of the current, so the speed of that river that we're rowing against. So we're going to choose x to represent what the first thing we're trying to find, which is rowing speed, and y is going to be what we're trying to find for the speed of the current. And this doesn't give you any equations, but we've got to just think about that a little bit. If you're rowing upstream, you're rowing against the current, so you're going to take your rowing speed and subtract the current speed, and that's going to be your overall speed. So whatever speed I row at minus the current, because it's working against you, that's going to equal 2 miles per hour when we go upstream. When we go downstream, it's just the opposite. I can take my rowing speed and add the speed of the current, because that current's going in the same direction, and that speed we found was 5 overall. So using those two equations, I rewrote those down here. This situation works better for elimination. You could also use substitution. It's easy enough to isolate one of your variables. But also, I could just add those equations together, and that gets me a cancellation. -y plus y, that would be 0. Could also take these equations and subtract. If I took the first equation and subtract the second, my x's would cancel, and we could find our y value first. So it's really up to you. If you want to add or subtract the equations, either way will work. But adding those equations, I get 2 x's, and again, the y's cancel. I get 2 plus 5 to be 7. All we got to do is divide by 2, and we get that x is 3.5. We were looking for two things here. We did need rowing speed and current speed. So you do got to make sure that after you get your answer for x, I plug that back into either of those two equations. I use the second one. And if I isolate for y, I also get my answer there. So we find that the rowing speed is 3.5 miles per hour. Current speed is 1.5. Should also work if you check your answer. If I take these and add those together, so 3.5 plus 1.5, I get 5 miles per hour going downstream. If I take my rowing speed and subtract the current, I get 2 for my speed going upstream. So let's also think about if my speeds were different there. So if the rowing speed in still water was 3 miles per hour and the speed of the current was 4, we won't really see that situation too much in our word problems, because what that would actually mean is that we start drifting backwards. We're not rowing fast enough to row faster than the current. So if you're trying to go upstream and you're not rowing quick enough, you're just going to be carried slowly down that river. So next question, same kind of situation, but this time we're talking about air speeds. With a tailwind, a bird flew at a ground speed of 3 miles per hour, flying the same path against the same wind. The bird travels the ground speed of 1.5 miles per hour. So we have to use that to figure out two things, the bird's air-speed and the speed of the wind. So that's our two variables. Again, x, we can just choose to say airspeed. Y would be our wind speed. And we want to break that down into two equations, just like your upstream and downstream. Same idea, just using air instead of water. So tailwind means the wind is going in your direction, so it's starting from behind you and going forwards. If I take my airspeed and add the wind speed, because that wind is working for me, that speed we found was 3 miles per hour. In flying against the wind, you might also see that called a headwind. So you have a tailwind and a headwind goes into your face and it's blowing against you. That means I take my airspeed and subtract the speed of the wind because it's working against you, and that's 1.5 miles per hour. So just like your last situation, if I set those two equations up, I think that will be easiest to solve using elimination. And just like the last one also, you could either add or subtract. I added those two equations, my y's cancel. I get 2x equals 4.5. Divide and we get our answer for x. And same as last time, I just got to plug that answer back in and find my answer for y as well. So we can use that to figure out the airspeed is 2.25 miles per hour and the wind speed is 0.75. So last situation we don't have to come up with a solution for, we just have to need to use some reasoning on this. One brand of cranberry apple drink is 15% cranberry juice, the other brand is 40% juice. We want to combine the brands to make a drink that's 25% cranberry juice overall. And we should be able to do this without calculating and see which brand we need more of. And the answer there is we should need more of the 15% brand, because if we're trying to make a mixture that's overall 25%, we just want it to be closer to the 15% mixture than it is to the 40. If it was more of the 40% mixture, you would expect a higher overall percentage for your mixture. So just make sure you have those complete. We'll work on some of those practice examples in class as well. And yeah, come prepared with any questions.